Okay, we already discussed the component level metrics, what is MTTF, MTTR, failure rate, and so on. Now let me continue with the system level models. These models take this component level metrics, component level information, and try to use it in order to obtain the reliability of entire system. And this group of models consist of reliability block diagrams, fault tree analysis, and event tree analysis. There are some other models, but in this presentation I want to cover this reliability block diagrams, fault tree analysis, and event tree analysis. And I will start with reliability block diagrams. These diagrams has been invented during this golden era of reliability, and the idea that a reliability block diagrams is a graphical depiction of the system components and connectors. The blocks here in the picture define the components, and the arrows define the connectors between these components. The components can fail during the system operation. And the idea is that the system is successful if any path through the system exists. So, for example, in the case, if we have the path from the beginning point to the end point through the system through the not failed components, it means that the system is okay. Otherwise, system fails. And according to the reliability block diagram, we can have a number of system configuration. The first is series configuration. In this configuration, the system components are placed one by one in line and sequence. And in the case of failure of one of these components, it means the system failure. So, if we know the reliability of these components, we can just, reliability is a probability that it will not fail. Then we can take a product of these reliabilities and obtain the reliability of entire system. The similar situation is for parallel configuration. However, in this case, the components are placed like in a parallel way, and we can think about these components as about the spare components. In the case if one of these components fails, the system still can functioning using the another one. So, and for example, we have a aircraft with two engines, and we know that even if one engine is failed, we can fly further using the another one. And for this kind of system, also, if we know the probability of failure for each of the engine, we can compute the reliability of the entire aircraft. The next configuration is K out of N parallel configuration. In this case, for example, we have the aircraft with three engines, but we know that we need at least two engines to fly further. So, and in this case, it means that as far as two of these three components are okay, we are safe. Otherwise, we failed. And we also can compute the probability of failure and reliability of the system using the reliabilities of the component. Well, it looks pretty simple. However, it's just a very high-level understanding of reliability block diagrams, and there is much more complexity inside, like combined configuration, as you see in the previous slide, complex configuration, inheritance, multi-blocks, and so on. Nested blocks when one component has a system inside and reliability block diagram inside, and it can be several nested levels, and so on. Well, the leading standard for the reliability block diagrams is IEC, International Electrotechnical Commission, IEC 61078. It describes how this reliability block diagram have to be drawn, how we attach the reliabilities, and how we can compute the reliability of entire system after all. This is international standard. And after that, you can see a number of national standards, like Australian standard, Spanish, British, German, and you can see that they use the same number, 61078. It means that they have been inherited from this international standard. And the last two standards are not from this series. It's independent standard, but they are also deal with reliability block diagrams. So, And here we can see a list of tools that can be used in order to build these reliability block diagrams and compute the reliability. The tools are provided by the majority of the software vendors, because it's pretty simple to develop these tools, and they are used in standards, so therefore majority of the vendors provide, develop and produce these tools. Okay, the next methodology is fault tree analysis. And this one is much more famous than reliability block diagrams. It was also developed in the middle of the previous century at Bell Labs, and originally it was developed for American military forces. So the idea of this technique is as follows. For a system, we build a fault tree. Fault tree consists of a top event, logical gates like AND or K out of AND gates and so on, and basic events. And usually these basic events are attached to the system components, to the failures or not failures of the system components. And for example, if we take a look into the left part of this tree, where basic event 1 and 2 is connected with AND gate, that means that in the case if both component 1 and component 2 fail, we'll have the failure of this part of the system because of this logical AND. And using the same logic, we can produce the Boolean expression for the top level event using these ANDs and ORs. And if we know the probability of failure for these basic events, for these components, we can compute the probability of failure of entire system using this logic. So, I think as you have already mentioned that the basic logic of the reliability block diagram and fault tree is pretty similar, and you're absolutely right. These two models are interconvertible. If you have a reliability block diagram, you can create a fault tree and vice versa. The difference is that reliability block diagram works in success space. It means that we imply that in the case if we have the path through this reliability block diagram, through the not failed components, we are okay. In the fault tree, it is we are thinking in opposite direction. If this Boolean expression returns true, it means we have a system failure. So, and usually the traditional solution for the fault tree is defining of the minimal cut sets. Minimal cut set is a unique combination of component failures that can cause system failure. In other words, we try to identify the minimal number of components or the critical number of components, and if these components failed, we will have the system failure. We try to identify them and the probability of this stuff and try to avoid this. And there is an extension of the fault trees called dynamic fault trees. And dynamic fault trees is nothing else as a fault trees plus functional dependencies plus hot, warm and cold pairs plus priority AND gate and plus sequence enforcement. I don't want to go in details, but the idea is that the fault tree is a static model, and it just shows the logic how the system will fail or not fail. And in dynamic tree we have the dynamics, the following dynamics. In the case of one component fail, the structure of the fault tree can be changed because of these pairs, priority AND gates and so on. And because of this dynamics, the typical solution is that we building this dynamic fault tree, attaching all the information to the basic events and so on, and after that we convert it to the Markov chain and compute the overall probability. So there is a little bit more, the number of standards for the fault tree analysis is bigger than the number of standards for the reliability block diagrams. However, the same situation, we have the leading IEC standard 61025 and a number of national standards. They also use this number. However, there are the other standards that describe fault tree analysis, like handbook, NUREC handbook, or INOR 21925. And in the right side of this slide, you can see the standards that actually require to use fault tree analysis. In the left side, you can see the standards that describe how to perform the fault tree analysis. And in the right side, you can see that this military handbook 338B and Society of Automotive Engineer IRP 4761, they require to use the fault tree analysis in the top-level reliability analysis. And because of this standard, the fault tree analysis is pretty important and are used everywhere. And because of this, actually, there are a lot of software tools that we can use in order to perform the fault tree analysis. The tools, the functionality of these tools are pretty the same. We can draw these fault trees, we can connect them. The difference is some of them have some specific gates and so on, but well, one more time, the functionality is pretty the same. And the last methodology in this group that I want to discuss is event tree analysis, ETA. And what is event tree analysis? Event tree diagrams provide a logical representation of the possible outcomes following a hazardous event. It means that we are thinking about the events that can happen during our system execution. So, and the event tree helps us to analyze different combinations of the outcomes of these events. For example, we have initial events, and the outcome can be okay or fail, and the same for each next event. And if we know the probability of outcome of a single event, we can compute the probability of the event combination or outcome of this event tree. So usually event tree model may be linked to the fault tree model by using fault tree gates results as a source of event tree probabilities. Okay, and in this slide you can see the comparison of fault tree and event tree. In the fault tree you can see we are talking about the brake system, and this system can fail either if brake sensor fails, or a brake controller fails, or a brake actuator fails. So, and in event tree we define three events: the failure of brake sensor, the failure of brake controller, and the failure of actuator. And if you know the probability of outcome of these events, and this is binary outcomes like failure or not failure, we can compute the probability of the combination of these events. That is the main idea of event trees and event tree analysis. So about the standards, the same picture. We have the main standards developed by International Electrotechnical Commission 62502, and we have a number of national standards. I would like to say that this method is not so popular as a fault tree analysis, and therefore a number of available software tools also is not so big. However, we can use RELX event tree. We can use event tree from the fault tree model of isograph, and the rest you can see in this slide.